Hey math fans, Alex here, and this time we're going to talk about a very special continuous random variable distribution called the normal distribution. Okay, so we're going to start off kind of by supposing that I have a PDF, and we're going to go and suppose that PDF looks a little something like this. So 1 over the square root of 2 pi times e to the minus z squared over 2. This is probably kind of a weird function. You probably never experienced anything like that before. And just to kind of sketch what the graph looks like, graph kind of looks a little something like, that's not what I wanted. Whatever. Okay, so the question that I want to ask is this even a valid PDF? Okay. You should always be skeptical if someone just gives you a weird looking function like this of whether it actually constitutes a probability density function. Okay, so we have to check that it normalizes to 1 over the entire real number line. So let's go ahead and do that. So to do that, we are going to check normalization. Mainly, we want to make sure that the integral from minus infinity to positive infinity of this proposed PDF, we need that to integrate to 1. All right, so we're going to go ahead and let I is usually the symbol denoted for the integral from minus infinity to positive infinity of 1 over the square root of 2 pi times e to the minus, I'm going to use x as my variable for reasons that'll become apparent. And we're not actually going to compute this integral. It's very, very difficult to compute. So instead what we're going to do is we're actually going to consider I times I. And remember that I squared is I multiplied by itself. And if I'm doing that, then it really doesn't matter what variable I use here and here, right? I could use x, I could use y for both of them, or I could use x for the first variable and y for the second variable, which is exactly what I'm going to do. This is going to be e to the minus, say, y squared over 2 dy. Okay, so we're gonna figure out what I squared is, which is actually possible to integrate. All right, so this is going to equal, and this is going to be by Fubini's theorem, which we've used quite a bit. We can go ahead and combine these integrals into kind of one double integral. Okay. Really doesn't matter which one comes first. Okay, but we're going to have this 1 over square root of 2 pi times 1 over square root of 2 pi. Not only is that going to be a 1 over 2 pi, but I'm actually just going to pull that out so we don't have to worry about it. And then we're going to have e to the minus x squared plus y squared all over 2. Doesn't really matter which one we integrate first. We'll say dx dy. Okay. So then one note about this integral in general is really you can kind of consider it as a double integral over some region which we'll call A, which is really r cross r, but it doesn't matter. It's some region A of this function, x squared plus y squared all over 2. And then this dx dy, we can go ahead and consider that as dA. Where in this case, A was a rectangular region given by the entire Cartesian plane. Okay, but why am I making it look like that? Well, we're actually going to make a substitution into polar coordinates, which isn't that bad. Okay. So we're going to go ahead and let x squared plus y squared equal r squared. And remember that dA was not the same thing as dr d theta, but it was, if you compute the Jacobian and do change of variables from Calc 3, you'll get that dA is exactly equal to R dr d theta. And that's going to make this integral doable. So this is now going to equal, and I'm going to change this up now. And now it's going to be equal to 1 over 2 pi times, and then I'm going to have a couple of integrals. This is going to be theta going from 0 to, we'll say, 2 pi, right? Because the integrating over all the real numbers is the same thing as integrating over all radii 0 to infinity, and integrating from all angles 0 to 2 pi. Whoops. So r is going to go from 0 to infinity. We're still going to integrate the same thing, but this time it's going to be e to the minus r squared over 2 r dr d theta. Okay. I'm going to just go ahead and take care of the d theta right now. Again, by Fubini's theorem, you can really just kind of split it up into regions and okay, maybe not as easily, but the d theta portion, since theta has nothing to do with this integral at all, I'm going to get a 2 pi out of that. So this is going to be 1 over 2 pi times 2 pi times the integral from r equals 0 to infinity of r e to the minus r squared over 2 dr. Okay. Now this is a Calc 1 substitution, and you can just kind of take my word for it. So these cancel to get me 1. And when I actually find the antiderivative of this, that's going to go ahead and be, okay, I'll just go ahead and do it. So we're going to go ahead and let's see, r squared over 2 be u. So then r dr equals du. Okay, so we have an r dr, so we can replace that with du, and we also have this, which we can just replace with u. So really what we have is that this is going to be the integral, well, we already computed the integral. Well, okay, so the integral of e to the minus u du, but we have to change bounds, but that's not too bad. Clearly, if r is equal to 0, then squaring it and dividing by 2, that's still 0. So this is u equals 0. And, you can argue as an improper integral, if this is going to infinity, then this is also going to infinity. So nothing too bad here. Okay, when you evaluate this integral, I'll just leave it to you to kind of verify that, but it's going to equal 1. Okay, that is a very important check to do, right? Because this is kind of a unique continuous random variable, and then you wouldn't expect that the integral over all real numbers would be 1. And since it is, this is a valid PDF. So now we can go ahead and just say yes. All right. Okay. By the way, some details I forgot to leave out. Sorry, I got ahead of myself. We only computed I squared was equal to 1, right? Because we had to square the integral to even make that possible. But that means that I is technically plus or minus 1, but why couldn't we have a negative 1 for the integral? Well, let's look at what we're trying to integrate. This is a positive function. E to anything, that's positive. Okay, we're multiplying it by a positive number. So if this is positive, the integral is surely positive, which makes it impossible to get a negative 1. Okay, so I equals 1 since the integrand is positive. Okay, so now we have verified that it is actually a valid PDF, which means we can kind of roll with it. So now I'm going to start off with the definition. definition. We're going to say that a random variable, which we're going to call z, it's very important that we call it z, PDF given by, really don't want to write it again, but I will. Okay, so pz of z equal to 1 over square root of 2 pi e to the minus z squared over 2. So that is said to have a standard normal distribution. Okay, and there is a symbol for that. Remember, uniform continuous had the little u, binomial, Poisson. Okay, different books will do different things. This book does not really do anything specific, but I'm going to go ahead and just say that that is going to be, z is going to be capital N for normal, and we're going to go ahead and say 0, 1. Why 0 and 1? Well, 0, it turns out, I'm just going to state it, the expected value of z turns out is 0, and the variance of z is 1. So that's why we call it 0 to 1. Okay, if we go back up here, it's not really unusual to understand why the expected value is 0, right? If it's a bell curve and it's centered around right here, well, that's all I need to do. All right, now let's go ahead and prove this. Again, these are things that should be proved and usually aren't. Let's go ahead and show that. I'm going to go ahead and show one of those really easily right now. Okay, so proof. You can just do the expected value right now. Might actually even do it in just one line. So the expected value, so to prove 1, the expected value of z is going to be the integral from minus infinity to positive infinity of z times the PDF. Why is this going to be one line? That's just 0. Why? Because that function, that's an odd function. Anytime that you integrate an odd function over this symmetrical region right here, you're going to get 0. Done. Now the variance, of course, is going to be a little harder. So let's do that. So recall that the variance of z is going to be the expected value of z squared minus the expected value of z quantity squared. Okay, but since the expected value of z, we already showed that was 0, really all we need to find is the expected value of z squared. Let's do that. Okay, so that's going to be the integral minus infinity to positive infinity of, I'm actually just going to pull this constant out, z squared e to the minus z squared over 2 dc. How are we going to integrate that? Well, it turns out that we're going to have to use integration by parts. And after kind of struggling with it for a little bit, what would you choose to make your u and what would you choose to make your v? Well, the integral, v has to be able to be integrated. That's the catch. And I can't integrate this. I can integrate this, but it's not going to make things better for me. So what do I pick? Well, I'm actually going to rewrite this in a more suggestive form. So this is going to be equal to 1 over square root of 2 pi. I'm going to expand the z squared out as z times z e to the minus z squared over 2. Okay, because now it's pretty clear that we're going to go ahead and let this be my u, and this is going to be my dv. Okay. So, let me just formalize that here. Okay, so u is going to equal z. V is going to be the integral of this guy. That's actually, Calc 1 integral. Okay, so that's going to be minus e to the minus z squared over 2. You can just kind of guess and check that too, right? Okay, so then integration by parts would get us that this is going to be equal to, well, let's see, u times v. So that's going to be u times v evaluated from minus infinity to positive infinity minus the integral of v. But v has a minus sign right here, so that's going to make this plus v du. But du is just going to be dc. Okay, now we're pretty much done because this is going to evaluate to 0. Okay, why? Well, this is going to grow very, very slowly. If you take any number, infinity or minus infinity, and square it, you're going to get a really big number. And e to the negative really big numbers is 0. Okay, so this is if you graph it as well, and in Desmos or something, you get 0, and then the c doesn't really matter since it's being multiplied by e to the minus function. Okay, and then what is this? Oh, I don't know how to integrate that. Oh, wait, you don't have to. This is the definition of well, this is almost the standard normal distribution, okay, with a small caveat. So in order to finish this up, I'm actually going to write this in a special way. I'm going to write this as the square root of 2 pi times the integral of this 1 over the square root of 2 pi e to the minus c squared over 2 dz. So the reason that I wrote it like that, and I actually kind of made a mistake, this should be multiplying this entire thing, right? So technically all of this needs to be times that, right? And all of this also needs to be times 1 over the square root of 2 pi. Okay. But now this integral, we've already evaluated it, right? We've already shown that the PDF, or the standard normal distribution, it normalizes. And it normalizes to 1. So that means that this entire thing is just equal to 1. Which means we're done, because 1 over the square root of 2 pi times the square root of 2 pi, that's 1. So the variance of this guy is really 1, and the expected value is 0. And those are all really important properties. Okay. All right, now that we've talked about the standard normal distribution, we're going to talk about just the regular normal distribution. Okay, so now we are going to go ahead and consider the random variable x. I'm going to tell you exactly what x is going to equal. X is going to be sigma times the random variable z plus this constant mu, which is essentially a change of variable here. And we're going to go ahead and note I'm going to argue that this is also a normal distribution. Okay, I'm going to tell you what that is in just a minute, but let's go ahead and see if we can find the expected value of x. Okay, so this is actually pretty easy. The expected value of x, that's just the expected value of sigma z plus mu. And using expected value properties, we can break that up into sigma, expected value of z, plus the expected value of mu. Okay, but the expected value of z was 0. So that's 0. And the expected value of a constant is just that constant. So we get that the expected value of x is equal to mu. What would the variance be? Well, remember with variance, we have to first calculate this. So let's just go ahead and do that. Okay, so this is going to be sigma z plus mu squared, which is going to be the expected value of sigma squared z squared plus 2 sigma mu z plus mu squared. Let's go ahead and break that up. So this is going to be sigma squared, expected value of z squared, plus 2 sigma mu expected value of z plus expected value of mu squared. Okay? Now, first things first, this term is 0 because the expected value of z is 0. This is the variance of z. Okay, you can go look up at the notes to verify that. And the variance of z is 1, so this is 1. So this is going to get us sigma squared plus mu squared. So the variance of x is going to equal this quantity. It's going to equal this quantity minus the expected value of x quantity squared. So it's going to be sigma squared. All right? So go through the details again if you need to, but I'm just going to summarize. Conclusion. The expected value of x was mu. The variance of x was sigma squared. Okay, so now I'm going to go ahead and make a definition. This should be the last one. Okay, so a random variable x with PDF given by, and here I'm going to go ahead and tell you what the PDF is going to be. This time it's going to be 1 over sigma times the square root of 2 pi times e to the minus x minus mu squared all over 2 sigma squared. Now, that might seem completely out of nowhere, but if you just look at this, and substitute in z, then the only kind of catch is that there's the sigma variable right here, which is the square root of the variance. Okay, but otherwise with this is said to have not a standard normal distribution, but just a normal distribution. And of course we have a symbol. It is symbolized as follows. We go ahead and say that x is distributed normal, has the normal distribution with mean mu and variance sigma squared. Okay, I already stated the properties above, so I don't feel like doing that again, but there we go. Okay, so here's kind of a comment about how to use this, practically speaking. Okay, so I guess comment or remark. In general, you always want your variable to be standardized. You always want to try to convert, that's not even an n, you want to convert the random variable x to z. Why? Because the standard normal distribution is just better to work with. I'm going to explain why. It's cleaner to work with both practically and computationally. From a practical standpoint, the expected value is 0 and the variance is 1. Those are very clean numbers. From a computational standpoint, I'm just going to go ahead and tell you the CDF of the random variable z, of the standard normal variable. It's going to be, remember, capital F of z, and by definition, that is the integral from minus infinity to z, and I have to use a dummy variable here, of 1 over the square root of 2 pi times e to the minus, we'll say y squared over 2 dy. Okay. Why is that better to work with? Well, you can't compute this integral. Don't try. Don't do it. However, computers have approximated this integral. And so that has been pre-computed by tables, calculators, and software. So anytime you work a problem, you always want to convert it to z, both from a practical standpoint, because back in the day when people, including me, used tables to figure out what the CDF up to a given z value was, we always use the standard normal distribution, and calculators find it easier as well. Also, from a theoretical standpoint, we're going to talk about the de Moivre-Laplace theorem. We're going to need to convert that to z as well. All right? So I'm going to do one example where I actually use the standard normal distribution. Let's see how we can apply it to a problem. Okay, so we're going to actually use the normal distribution here. It says that assume that during seasons of normal rainfall, the water level in feet of a particular lake follows a normal distribution with mean 2,000 feet and variance 0.64 feet. Okay, so I didn't really sketch out the normal distribution. I sketched out the standard normal, but the actual normal distribution is going to be something like this. That is the worst bell curve ever. God, I'm so ashamed. Okay, where this is the mean, whatever that is. In this case, we have 2,000 feet as the mean. And it's going to be plus or minus the square root of this variance. So we're going to find that in just a bit. Okay, so part A, during a season, would it be unusual to observe a water level of at most 1999 feet? Okay, so the idea here is we want the probability that x is, let's see, at most 1999 feet, so less than or equal to that. Well, remember what I told you. I told you to always use the standard normal distribution. So first thing that we should probably note is that x is normally distributed with mean 2,000 feet and variance 0.64 feet. And also, since sigma squared is 0.64, that means that sigma is going to be the square root of that, which is going to be 0.8. Right? So what this is saying is typically the water levels are around 2,000 plus or minus 0.8. Anytime you hear someone say plus or minus, they're really talking about this quantity. Okay, and let's go ahead and compute this. So always convert to z. I'm going to show you how to do that. So since we want x to be less than or equal to 1999, to convert to z, we have to do what? Z is going to be x minus mu divided by sigma. Okay, so I should also comment that z is equal to x minus mu divided by sigma. So keep that in mind. Okay, so what are we going to do? Well, we're going to go ahead and subtract the mean, which is 2,000, and divide by sigma, which we got as 0.8. We're going to do the same thing to this side. Subtract 2,000 and divide by 0.8. Okay, but then the quantity on the left is by definition the standard normal variable z. We converted it correctly. And the stuff on the right-hand side, when I computed that, I got minus 1.25. Okay, so we get that the probability that x is less than or equal to 1999, that's the same as the probability that the standard normal variable z is less than or equal to minus 1.25. Since we want the probability of something leading up to, so everything leading up to minus 1.25 is what we're interested in. That is really the CDF evaluated at 1.25. And I don't know what that is, but I know someone that does. The internet. So I'll be right back. Okay, so the idea is what you can do here is we can go ahead and plug in the value of z. Well, in this case, we got minus 1.25. The mean is 0. The standard deviation was 1. That's the same thing as the square root of the variance. When you hit calculate, it just gives you the answer. That's the CDF. Now, computers are more sophisticated nowadays, and yes, it does allow you to pick non-zero mean and all that stuff, but really you want to work with z, so please convert to z. Okay, so we got 0.1057. So this is 0.1057. All right, so let's think about that for a second. Would it be unusual to observe a water level of at most 1999? Okay, so if it's plus or minus 0.8, then this would be maybe 1999.2. This would be 2000.8. Okay, so a lot of the data is going to be over here. I'm actually going to have you do an exercise to figure out approximately how much data. But at most 1999, well, we're looking for maybe somewhere over here. So it's plausible that that's about 10%. All right, part B, suppose the water will flood if the level exceeds 2002 feet. What's the probability of this occurring? Well, if this is 2000.8, we have to go a couple more sigmas to get to 2002. So you might predict that that probability is low, but let's just do it again. So we want the probability that x exceeds 2002. Okay, but that's the same thing as 1 minus the probability that x is less than or equal to 2002. I'm just going to go ahead and have you kind of verify as an exercise that this is equal to 1 minus the probability that the normal variable z is less than or equal to 2.5. So just do the exact same thing that I did. Okay. So this is equal to 1 minus the cumulative distribution, where you plug in 2.5. This is going to be very close to 1, which makes this very close to 0. And when I typed it into StatTrick, I got 0.0062. So pretty unlikely the lake will flood. Okay, in the next video, we're actually going to do a little bit more theory, and we're going to take the binomial distribution and see how that's related to the normal distribution. Hope to see you there, and have a great rest of your day.